Hello students. As you know, we have already started Ionic Equilibria. Okay. Now the next point we are going to say amphoteric nature of water. Amphoteric nature of water means water behaves as acid as well as base. Say amphoteric nature of water means the ability to behave as base as well as acid. Such behavior is known as amphoteric nature of water. Now to just clear the amphoteric nature of water behaving as acid and base, let us see two examples. In the first example, water behaves as acid. In the next example, water behaves as a base. Now here OH2O, when combines with NH3 ammonia, then formation of OH minus and NH4 plus. Here NH3 ammonia molecule accepted one proton from H2O molecule to form NH4OH. So H2O is a proton donor to other molecules. So it is here acts as acid. Now in the next example, when H2O reacts with HCl, formation of H3O plus hydronium ion plus Cl minus. Now H2O is converted to H3O by accepting one proton from HCl. So here in this example H2O acts as a proton acceptor. So here it is as a base according to Lovren-Bronsted theory. Now say that is this is the amphoteric nature of water. Okay. Now H2O acts as an acid towards NH3 and acts as a base towards HCl. Therefore H2O is amphoteric in nature. Okay, so this is all about the amphoteric nature of water. The next point is ionization of acids and bases. Acids and bases, they ionize. Acid, bases and salt, when dissolved in water, they ionizes into ions. Okay, now acid and bases are classified as strong and weak electrolytes depending upon the extent of dissociation. Okay, as you know, strong electrolytes, acids or bases, they almost completely dissociate in water, whereas weak electrolytes, acids and bases, partially or very feebly dissociates in aqueous solution, in water solution. Now let us say these examples of strong acid and strong bases. HCl is a strong acid which dissociates to give H plus and Cl minus, and NaOH as a strong base dissociates to give Na plus and OH minus in their aqueous solutions. Now these two equations are shown by a single arrow in the forward direction. That means they are completely dissociable. All the molecules of strong acid, this strong base is converted to into their respective ions. These are the few that examples we have taken. Now just nitric acid, H2SO4, HBr and HR are also the examples of strong acid, and potassium hydroxide along with NaOH is also example of strong base. Now these are the example of weak acid and weak bases. The example of weak acid is CH3COH. When dissolved in water, it forms CH3COO minus and H plus ion. And NH4OH as a weak base, it dissociates to give NH4 plus and OH minus. And both of the equations are shown by the double arrow forward as well as in the reverse direction. That means there is the equilibrium is formed between the undissociated molecules and the ions formed, is it? And this is being a weak electrolyte, weak acid as well as a weak base. Okay, now let us say the next point, that is of dissociation constant of weak acid and weak bases. See here, dissociation constant of weak acid and weak base. Okay, what is first of all let us say what is a dissociation constant. Dissociation constant, basically it is a equilibrium constant applied for the dissociation equation of acid and base. Now let us consider, let us first of all see the dissociation constant of weak acid. Weak acid here is denoted as Ha, where H hydrogen is present, which dissociates to give H plus. Now Ha, weak acid, is gives H plus, proton plus A minus, negative ion, cation and anion. Now the equilibrium constant called as dissociation constant for this equilibrium acid dissociation constant Ka is given as the product of the products, the product of the concentration of products divided by the product of the concentration of reactants. Is it? That's why H plus into A minus divided by HA, concentration of HA. Here K is the dissociation constant of acid, which is the equilibrium constant. Now similarly, weak acid is denoted here BOH, which is consisting of OH minus ions. Now BOH dissociates to give B plus OH minus, being it is weak, so it partially dissociated into ions. Now equilibrium constant called as base dissociation constant for this weak base is written as Kb is equals to the concentration of B plus into the concentration of OH minus divided by the concentration of BOH. So what is equilibrium constant? It is the ratio of the product of concentration of the products divided by product of the concentration of reactants. Okay. Now this is the equilibrium constant, the acid dissociation constant of weak acid HA, and this is the base dissociation constant of weak base. Okay, so dissociation constant for weak acid or weak base, this is the definition. So how it is? The dissociation constant of weak acid or weak base is defined as, it is the equilibrium constant for dissociation equilibrium of the weak acid or weak base. Okay, so this is about the dissociation constant of weak acid or weak base. Okay, now let us study Ostwald's dilution law. Now see here, Ostwald's dilution law is applicable only for the weak electrolytes, weak acids and weak bases. Okay, basically this Ostwald's dilution law is the quantitative expression or quantitative extension fact for the Arrhenius concept of acids and bases. Okay, now let us see how the Ostwald's dilution law is applicable for weak bases. Actually, Ostwald dilution law is that provides the relation between alpha, that is degree of dissociation of weak acid or weak base, and the concentration as well as volume. Okay, now here let us say the Ostwald dilution law for the weak acid HA. HA is a notation of a weak acid, general representation of the weak acid, which contains hydrogen atom or H plus ion. Now HA as usual dissociates partially to form H plus A minus. Being it is weak, there is the equilibrium is attained after some time. Now acid dissociation constant, as previously we have saw, that Ka is equals to H plus concentration into A minus concentration divided by HA. Let 1 mole of HA is initially present in V dm cube of solution. That means only 1 mole of a solution is dissolved in V liters or dm cube of the solution, and alpha is the degree of dissociation. What is alpha? Degree of dissociation. And alpha is defined as, it is the fraction of the total number of moles of an electrolyte which are weak electrolyte which are dissociated at equilibrium, right? So alpha, these are the fraction which are dissociated at equilibrium, right? Now HA, this equation I have written as it is, initial moles, as here we have just considered 1 mole, and no dissociation, before dissociation 0, right? At equilibrium alpha number of the ions are dissociated, splitted into ions. That's why 1 minus alpha, these are the moles, 1 minus alpha moles are left behind after equilibrium, right? Now concentration is number of moles divided by volume is the concentration. So 1 minus alpha upon V is the concentration of HA at equilibrium. Alpha upon V is the concentration of H plus, and alpha upon V is the concentration of V minus. Because coefficient of both of are 1, number of moles of equal, that's why the concentration is also equal. Now this concentration is substituted here in this equation. H plus concentration, A minus concentration, and HA concentration, right? The equation becomes K is equals to alpha upon V into alpha upon V divided by 1 minus alpha upon V. This is the concentration of this H plus, A minus, A plus, okay, HM. Now this VV, 1V gets cancelled with 1V. The equation will be equal alpha square upon 1 minus alpha into V. So K is equals to alpha square C upon 1 minus. Here 1 minus, here where 1 minus V is equals to C. Concentration is number of moles per dm cube, right? So here 1 upon V is written as C directly. So K is equals to alpha square into C upon 1 minus V. As V is very small, see, that is sorry, this alpha, what is alpha? Alpha is the degree of dissociation and it is very small, right? Alpha is very small, that's why 1 minus alpha is equals to, nearly equals to 1 we can consider, okay. So here we can write 1 minus alpha can be neglected as it is 1. So K is equals to simply alpha square into C. This equation is rearranged for alpha. It will become alpha is equals to under root of K upon C and alpha is equals to K into V, because 1 upon C is equals to V. That means the statement can be made in the case of weak electrolyte of Ostwald dilution law, weak acid. The statement of Ostwald dilution law in the case of weak acid can be made from these equations, okay. That means it implies that the degree of dissociation of weak acid is inversely proportional to the square root of its concentration, or it is alpha is directly proportional to the square root of dilution or volume of the solution containing 1 mole of the weak acid. So this is the Ostwald dilution law which we have studied in the case of weak acid. Now let us see for the weak base. For the weak base, okay. Now see here weak base, it is considered a the steps are as usual in the case of, we have seen in the case of acid. Here only the notation is different, that is base is represented as BOH because it contains hydroxyl ion OH. So it dissociated as BOH to associates to give B plus and OH minus. Base dissociation constant we have seen as written Kb is equals to B plus OH minus upon BOH. As usual, let 1 mole of the weak base is present or dissolved in V dm cube of the solution, and where alpha is the degree of dissociation. Degree of dissociation is fraction of the total number of moles which are converted into ions, means alpha is equals to number of ions as the statement. Now this equation is written as it is: initial number of moles 1 mole as we stated considered, and before dissociation 0 0 number of cations and anions present in the solution. Now at the equilibrium number of moles, if alpha are separated splitted as per the definition of the degree of dissociation alpha, number of moles present left behind BOH are 1 minus alpha at equilibrium. So the concentration is written Concentration, number of moles divided by volume is the concentration. At equilibrium is 1 minus. The concentration is here, as we have seen, 1 minus alpha upon V, alpha upon V, alpha upon V. Substituting the values of concentration here in this equation, we have read as usual in the previous case, alpha upon V divided by 1 minus alpha upon V. 1 V gets cancelled with this V, alpha square upon 1 minus V into 1 minus alpha into V. Now here 1 upon V is concentration. That is, you just remember, C is equals to either 1 upon V simply, or V is equals to 1 upon C. This 1 upon V is C. But this 1 minus alpha is alpha. The degree of dissociation alpha is the fraction, very small. So 1 minus alpha is taken as nearly equals to 1. This term is neglected. Kb is equals to alpha square into C. Kb is the base dissociation constant, or dissociation constant of base. This equation can be rearranged for alpha. Alpha is equals to under root of Kb into V. Alpha is equals to Kb upon C. That means the degree of dissociation of weak base is here we just, the degree of dissociation alpha of weak base is inversely proportional to the square root of volume, and or it can be stated as alpha is equal to just a moment. So from this equation, this can be rearranged for alpha as alpha square is equals to Kb upon C. Taking the square root, this can be written like this way, and 1 upon C we have seen V. That means alpha is the degree of dissociation of weak base is directly proportional to the square root of volume, or the degree of dissociation of weak base is inversely proportional to the square root of dilution. That is the concentration. Now see, you just refer the textbook and go through the points, study well. Best of luck.